Hi everyone, I'm Professor Burgesser, and in this video we're going to be looking at how we apply our momentum-impulse relation to solve problems in which we don't want to worry too much about the internal forces in whatever system we're looking at. So just as a reminder, when we're talking about the momentum-impulse relation, we're looking at the change in momentum, the final minus the initial, and that's equal to the external forces acting on a system times whatever time frame that we're looking at in which the momentum has changed. And the reason this is an important relation is that in this case we don't have to worry at all about the internal forces in our system. So those can be as complicated as they can be and we don't have to actually calculate them. All we worry about is the external force acting on the system. So if we can measure the total momentum before and after some event, then we can actually apply this relation and solve for the motion of the system in future times. So we're going to look at a couple problems and we're going to follow the same procedures that we've been looking at for our previous problems using kinematics, forces, and energy, but with some modifications to take into account to our momentum-impulse relation. So as before, we're going to set up our problem by looking at what are the knowns, what is the target quantity we're trying to solve for, and if there's any predictions we can make about the result before we actually go about and calculating. Then we're going to break up our problem into a series of acts, and this is important because it allows us to look at what happens at these change points for momentum. So we can identify those events and just look at the before and after, then we can solve step by step. Then we're going to define a system for each of those acts because sometimes maybe the characters involved in the act is going to change, so we want to make sure we define that carefully. We're going to calculate our initial and final momentum for the system for those characters if we know them or set up the unknowns, and then calculate any external forces that are happening on the system during this collision or exchange of momentum. And then we're going to use our momentum-impulse relation, solve for our unknowns. We may have to go then for these other acts to use our procedures of kinematics, forces, and energy to solve for those motions. And of course, in the end, we want to check our solution to make sure that it matches the units that we're looking for, it matches the predictions that we had made, and we can test it for different extreme cases if that's a way of making sure the relationship is what we expect. So let's start from an example from sports and look at the case of injuries that happen in the sport of baseball. Maybe if you're a sports doctor, you might notice that a lot of catchers are coming in with wrist and hand injuries. And to inquire about what's going on, you may want to figure out what are the forces involved on the hand in the act of catching fast pitch balls. So this is the sort of question we can ask. We can look at the case of a baseball being thrown at 100 miles an hour. If there's high-speed footage of that catch, we can see how long it is, the time span it is for the ball to be sort of stopped, and then we can look at what the forces are using our momentum-impulse relation. So let's start by first writing down what are knowns, doing our general setup here. So the things that we know are the mass of the baseball, which is given as 150 grams. We also have a speed of the baseball, which is equal to 100 miles per hour. And that's not in our SI units, and so we should convert that over. And the conversion factor is 0.45 meters per second per 1 mile per hour. And so that equals 45 meters per second for our initial baseball speed. And then we're also given the time of the momentum change as 10 milliseconds, or 10 to the minus 2 seconds. All right, so that's going to be important when we write down our momentum-impulse relation. Now, the thing that we want is the external force acting on the hand as a result of stopping this baseball. And we'll talk a little bit at the end here and where that actual external force comes from. But that's the force we want to look at in terms of the injuries. Now, the next step is to sort of look at how this problem sets up into different acts. And in fact, there's really just one act in this problem. So if we look at our act structure, there's just one event, which is the catching the baseball. And that's, of course, the case where we're going to change the momentum from whatever the initial momentum of the baseball is when it's thrown to 0. And so we're just looking at that change as our only event in this case. And of course, then we can also look at what the system is for our momentum impulse, and that's going to be the baseball and the mitt or the hand that we're looking at in terms of this momentum interaction. And we can also make a prediction of what the force is going to be. And if we just think a little bit about how many times catchers catch baseballs, the force is going to be, of course, quite high if it's causing injury, but it can't be so high that every time a catcher catches a baseball they break their wrist. Otherwise there won't really be much of a game anymore. So it should be a reasonably high but tolerable level of force. And when we look at our numbers, we'll see whether that really makes sense in terms of what we expect the tolerable force would be for the forces acting on our hands. So let's start our solution by looking at our first and only act, and that's the case where the change in momentum is caused by an external force. Okay, and that's the number we're going to actually calculate. And so we can look at this by comparing the initial momentum of our system to the final momentum of our system. I'm going to make one more assumption here. I talked about the speed of the baseball being 100 miles an hour. That's given to us. I'm going to also assume that, let's put this right here, that the initial speed of the mitt is equal to 0 meters per second. So we got to make sure we have a speed for that part of our system. So if we write down the initial momentum, it's really just going to be the mass of the baseball times the speed of the baseball. Now, I forgot to do one thing here. I wrote this baseball's mass in terms of grams, and of course that's not our SI unit of mass. So let's make sure that we convert it into our kilogram unit, so it's just 0.15 kilograms. And so now we can actually go ahead and plug that into our expression for momentum. So 0.15 kilograms times 45 meters per second, and this is equal to 6.8 kilograms meters per second. And of course we don't have a momentum for the mitt if we're assuming that it starts off at 0 meters per second. Now let's write down our final momentum. Well, that's going to be the case where the baseball comes to rest, and so has the mitt. So that's easy. That's 0 meters per second. Now notice that this is clearly not equal to each other, so this can't be a conservation of momentum problem. We definitely have to have an external force on our mitt ball system in order to have this change of momentum turn out in this direction. Okay, so we can just now write down our impulse momentum relation. So delta P is just PF minus PI, and that's just minus 6.8 kilograms meters per second. All right, minus because we are losing momentum out of the system. And this is going to be equal to our external force times the time frame over which this momentum interaction occurs. And that's just equal to our external force times 10 to the minus 2 seconds. And so we can solve for our external force by just dividing by 10 to the minus 2, which is just multiplying by 100. Dividing by seconds is going to give us kilograms meters per second squared. And so this turns out to be 680 kilograms meters per second squared, which is, of course, our unit of newtons, which is the unit of force. All right, so we've got our number. So now the important step, of course, is to make sure that this is a number that makes sense. So 680 newtons, if you recall that a typical body mass is something like 70 kilograms. And so if we multiply that by g, which is 9.8 meters per second squared, we get a number that's of order 700 newtons. So the force that's exerted by the wrist catching this ball and stopping it in about 10 milliseconds is equivalent of you standing on your hands, or more importantly, standing on one hand. Of course, it's not for a whole period of time. So that's a force that's tolerable, but of course, if you kept standing on one hand for a long time, you could expect to get some injuries in your wrists and hands. So it's not surprising that catchers have these injuries because the forces involved are about the level you'd expect to have, not necessarily immediate damage, but certainly damage over a long period of time. Now, just to complete this, remember I mentioned that we want to figure out where this external force comes from. The ball in the mitt is our system, so it's not a force that's coming from the ball because it's within our system. That external force is really the force of our arm holding our hand in place. That's the external part of the force that's coming in to our hands. So not only do we have to worry about the injuries on our hands, but we may also have to think a little bit about the injuries happen on arms, which are providing the external force of 680 newtons to slow that ball down in order to catch it. So let's look at another example, in this case that has multiple acts to the problem. And this is an example where we're going to look at what happens when an object collides with another, sticks to it, and then causes the whole system to move in some way. The system I'm setting up is a munitions test that's done in some cases where you want to measure the speed of a projectile, and you can do that by shooting the projectile into essentially a container, which then is suspended and can swing up just like a regular pendulum. And so you can measure the angle of that pendulum swing and back out from that what the speed of the initial projectile was. So I've set up the problem as follows. We have a pendulum of length 2 meters, about 6 feet, and then we've got a projectile, fairly heavy one, moving at about 5, with a weight of about 5 pounds. And then the cup, the container, is going to have a weight of 50 pounds. And then we want to see what is the speed of that projectile if this whole system slides up by about 15 degrees. So let's follow our procedure and start by writing down our known values. We've got quite a few of them. We've got the mass of the projectile, which I'm going to call MP. That's written as 5 pounds. Now, of course, we have to be careful here because pounds is really a measure of weight, which is a force. So it's not really the mass. We've got to convert it to kilograms, which here on Earth is the conversion factor 0.45 kilograms is equal to 1 pound. And so that works out to be 2.3 kilograms for the projectile. All right, so just to make sure it's clear, we've converted a force into a mass. Because of the constant gravity of Earth, we can directly convert that. We've got the mass of our pendulum cup, which is 50 pounds. And of course, that's going to have the same conversion factor, so that's 23 kilograms, just a factor of 10 different. We're given the length of our pendulum as 2.0 meters, and we're given a final angle for our pendulum of 15 degrees. All right. Now, also implicit in this problem, of course, is that we have gravity acting downward on the system. That's what's going to cause the pendulum to slow down as it swings upward. Okay, and then what do we want to solve for? What we want is the initial speed of the projectile, right? And of course, that's going to be something that we can get out of the momentum that we calculate for that projectile as it's coming in. Now, let's set up the actual storyline of this problem. What are the acts involved? And if we think about it, there's actually 2 acts that happen. The first one is when the ball collides with the cup, all right? There is a convergence of the system there. And so that's kind of the first act, is the collision of projectile and cup, all right? And of course, the forces involved in that collision may be hard to discern, but let's assume that we don't have to worry about that because we can treat it as a system and not worry about the internal forces. Once that ball is in the cup, then it's going to swing upwards, and so this then becomes a pendulum motion for the combined system. Right? So both the cup and the ballistic ball are going to swing up, so we can approach that from our regular pendulum motion solving problems. We'll look at a couple ways we can do that. All right, and then so based on those acts, we can define our system to just be the projectile and the cup or the pendulum. And we can make some predictions about this motion. When we think about this, if we've got a 5-pound weight that's coming in to a 50-pound weight, that's a big jump up in mass. It still causes the pendulum to swing up. So I would suspect that the projectile is actually moving pretty fast in order to have that much of a effect on the swing of this very massive thing. So this is a very vague prediction, but I'm going to guess that the speed of projectile is relatively fast. And I guess that's a little bit qualitative, but at least gives us some idea of where we would expect to see our number to head at the end. Okay, so now let's go ahead and start to solve our problem. We're going to do that by starting with our different acts, and we'll start with the first act, Act 1, the collision. And this is the case where we're going to look at the change in momentum is equal to our external forces times the change in time. All right, so let's write down what the momentum are before and after the collision. So initial momentum is just contained within the projectile. So that's the mass of the projectile, mp, times its speed, mp, which is the thing we're trying to solve for, plus the momentum of the cup. But at this point, the cup's not moving. It's just sitting there suspended. So that's equal to 0. And so we can actually solve for this. This is going to be 2.3 kilograms times the speed, which we don't know. So I can't put that in parentheses, but we'll put it there anyways. All right, and so that gives us a number for our initial momentum. We can write down our final momentum, and that's going to be the combined speed of both the cup and the ball. So we'll mp plus m cup times its combined speed, which I'll just call v for now. And again, we don't actually know this number. We can write down the masses. It's just 2.3 times plus 23. So that's 25.3 kilograms times our final speed. But we don't have any other information to solve for that. We're going to equate that difference to the external forces. And if we think about it, we do have some external forces acting on the system. Let's draw a quick force diagram on the system of our cup and our ball at the same time. And if we think about it, there's a couple forces. Of course, there's the combined weight of the cup and the projectile times gravity. And there is a tension force that's acting on the pendulum, and that's pointing upwards. But at this stage, as there's just making contact here, there's no other external forces that are acting in a horizontal direction on this problem. And so all the external forces are in the, let's call this the x hat, or sorry, into the y hat direction, if we choose y hat to be the vertical direction. Okay, so they're in the vertical axis. And that's perpendicular to our initial momentum and our, in fact, final momentum in the particular collision we're looking at. So that means that we can ignore these forces because they're not acting in the direction to change momentum along this horizontal axis in which we're looking. So in fact, what we have is a conservation of momentum problem, at least along the x direction. And so we can solve for the, let's solve for the pendulum motion here, because that's the thing we're going to solve for eventually. That's going to be equal to 25.3 kilograms divided by 2.3 kilograms times the speed of the whole system as it moves upwards. And that ratio works out to be something like 11 times the speed. But at that point, we're still stuck because we don't know what the speed of the pendulum is after after the projectile hits it. So we're going to have to now go to our next act to see if we can solve for that problem. Let's proceed on to our second act and look at what happens in the motion of the projectile in the cup as it swings up on this pendulum motion. Now we've seen this before, and we can solve this with our energy approach. So we're going to look at the energy, and in fact we're going to look at energy conservation because we haven't identified any dissipative forces in our problem. There's no friction or viscosity that we're worried about. And so we can simply equate the initial energy to the final energy and solve for our unknowns. So our initial energy is going to be contained in the kinetic energy of the cup and pendulum system. So this is 1/2 times the sum of the two masses times their combined velocity squared. And I'm changing my notation just a little slightly here, so let's make sure we get it consistent with what I have above. That's VPC, which is the combined speed of those two objects, squared, because that's kinetic energy, plus the potential energy. But if I assume that where I'm starting at the bottom of my motion, that's my 0 point for my potential energy, we can just set that equal to 0. Okay, so then we can write down our final energy, which I'm going to write right here. That point we're going to assume is the point where the pendulum swings and stops. And so our initial kinetic energy is going to be, or sorry, our final kinetic energy is going to be 0. But our final potential energy is going to be the sum of the masses again, times g times their height. Now, what is that height value? Well, let's just do a quick geometry diagram here. Initially, we start this pendulum suspended straight downwards, and that pendulum has a length L. And it swings up by about 15 degrees. And so what we're looking at is this little segment of height right there. Now if I draw a leg there so I can have a nice right triangle in my diagram, you can see that this height is equal to the full length of the pendulum minus this side of our triangle. And since this hypotenuse is also L, that side of the triangle is just L times cosine of the angle, right, the adjacent side. So I can write down our expression for the final energy as just, again, the sum of the masses plus, or times g, times the length of the pendulum times 1 minus cosine of our final angle. All right? And again, because we don't have any dissipative forces in this problem that we're looking at, we can set these equal to each other, which allows us to cancel out a couple of terms, and more importantly, write down our velocity in terms of the other things that we know. So I'm going to multiply by 2 and take the square root. So this is the square root of 2gl 1 minus cosine theta. And if I put in some numerical values here, we've got 9.8 meters per second squared for g. We have a length of 2 meters for the pendulum. And 1 minus cosine theta, this is cosine of 15 degrees, which is about 0.97. So this turns out to be 0.034. All right, and if we calculate that number completely, we end up with 1.34 meters per second for the speed of the combined projectile and cup just as it's about to swing up. And that's because it reaches an angle of 15 degrees. Now, we can go back to our first act and realize we can just now write down then the projectile speed is just 11 times that, and that works out to be about 15 meters per second, and that's the solution of our problem. Now, just to get an idea whether this matches our predictions, 15 meters per second, there's about 2 or so miles an hour per meters per second, so this works out to be about 32 miles per hour. And indeed, that seems like a relatively fast speed for a projectile, particularly something that's 5 pounds. And so that's at least qualitatively consistent with the expectation we had for this projectile motion. A fun annual tradition here at UCSD is the pumpkin drop that happens off either Tioga or one of the other buildings on campus. And that drop is a large pumpkin that's tossed off a building. And on impact, it explodes into a gazillion pieces. And one of the things, if you are in charge of this particular event, is to find out how far are these pieces going to spread out so that you make sure that there's nobody standing in the way from a rapid piece of pumpkin coming at them. So we can calculate this using our momentum impulse formalism by looking at what is the momentum of pieces that are coming off upon impact based on some assumptions of the energy and the momentum of the system. So here's my setup. I'm going to take a 100-pound pumpkin and drop it off a 7-meter building. And let's assume that when it hits the ground, it just breaks up into 2 pieces, and so instead of lots and lots of pieces. And those 2 pieces fly apart from each other. And one piece is 20 pounds and one piece is 80 pounds. And we're going to make a simplifying assumption, although this is actually a fairly bad assumption, that we haven't lost any energy as a result of the collision. Of course, we do lose lots of energy because you can hear the impact. That's sound energy, pressure energy coming away from that particular interaction. But just to keep things simple, let's assume that we haven't lost any energy as a result of this collision. So let's start this as before. We're going to look at what we know. Our known values include the mass of the pumpkin. Well, we're given the weight of the pumpkin as the 100 pounds. And again, we can convert that using our Earth-based conversion of kilograms to pounds, because pounds is a force. And so that works out to be 45 kilograms for our large pumpkin. We're given an initial height of 7.0 meters from which the pumpkin is dropped. And we're told, at least given this problem, that this is an energy conservation problem because we're said that the change in energy is equal to 0 on impact. So that's an assumption that we're going to make use of in order to actually calculate some of the speeds. What are we trying to solve? Well, we want the speed, the final speed of the small piece of pumpkin, the 20-pound piece of pumpkin. And we also can define sort of a system of acts here in which this sort of story unfolds. Now, we're starting with the pumpkin at some height. We're letting it drop. That is one act of motion. And then on impact, the pumpkin kind of explodes. That's sort of our second act. So act one is the drop, which is really ballistic motion, because we have a constant acceleration from gravity. Act two is the change in the momentum on collision with the ground. And of course, this is hitting the ground, so there are external forces acting, but we'll see if those external forces have any effect on the horizontal motion of the pieces of the pumpkin. Of course, our system is the two pieces of the pumpkin, which initially are together as the pumpkin is falling, but of course fall apart upon collision. So that's the system that we're going to be looking at. And we can make some predictions about the motion. It's very hard to make a prediction of the speed, but we can say that the speed of the small piece is probably going to be bigger than the speed of the big piece, just because of what we know about how momentum is transferred between objects of different masses. And it's probably going to be high speed, but we'll see if that's actually the case. Okay, so in the last problem, we step by step. We started with the first act, we went to the second act. Just for some variety, let's start with the second act and then back our way up to the first act and see if that gives us any different way of solving the problem. So we're going to start with the collision first, and that's collision upon impact. And so this is looking at the change in momentum is equal to the external force times delta t as vector quantities. So let's look at what our initial momentum is, and we're going to focus on the horizontal motion, because that's the motion that we are asked to solve for at the end, that horizontal motion. So let's focus on that alone. In that case, the initial momentum is equal to 0 because the pumpkin starts dropping straight down. It's got no speed left or right, and so it's going to be 0 upon that impact. Of course, the final momentum is very different because we've got momentum from both objects. So let's say we've got some initial speed for the 20-pound mass. We'll call that V, what do we use for our thing? VF, small, all right? And we've got some speed for our large piece. We'll call that VF big. Now I've added these together, but if you think about it, these things will probably be acting in opposite directions because they are moving apart. And so we will have to, in the end, see that, make sure we verify that by making sure one of these velocities is going to be a negative number. Now, so that's the final speeds. Let's look at, we don't know at this point whether they're conserved, but let's look at the external forces acting on this pumpkin at this point. And again, we can do this by drawing a force diagram of our pumpkin and looking at what forces are acting right at the point of impact. Well, we certainly have the mass or the weight of the pumpkin, again that 100 pounds, and it's come into contact with the ground, so there's now a normal force that's pushing up to it. But in terms of external forces, that's really it, right? Nobody's off the side pushing the pumpkin left or right. And so all of these forces are all perpendicular to the momentum direction that we're interested in. These are perpendicular to PI and PF, and so we can ignore this, for our delta P here. So that means that these two terms are equal to each other, so this is equal to 0, and that allows us to solve at least for the relationship between the small speed and the large speed. So I'm going to actually change my notation here. This is the speed of the 20-pound mass is equal to the mass of the 80-pound piece divided by the mass of the 20-pound piece times the speed of the 80-pound piece. And of course, that's equal to 4 times the speed of the 80-pound piece. So at least figured out, we've confirmed our prediction that the small piece is moving quite a bit faster than the large piece by a factor of 4. But at this point, we don't have enough to actually solve for the number itself because it depends on another unknown. So now we're going to have to back up to our first act to see if we can figure out what is the speed of this system as it is just before it hits impact. What drives the speed of these two pieces as they fall apart? So let's go back to Act 1, and that's looking at the drop of the pumpkin as it falls down. All right, in this case, we can do this as an energy conservation problem again. because this is just the free fall motion of the pumpkin from the top of the building. We haven't identified any viscous forces, air resistance, drag resistance, anything like that, which probably act, but perhaps not enough over this very short span of distance. And so we can assume that that's going to be negligible and just look at the conservation of energy for the pumpkin itself. So its initial energy is again equal to the kinetic energy plus the potential energy. Remember that we're starting this pumpkin from rest at the top of the building and then letting it fall down. And so that's going to be equal to 0 plus our mg times h, where h is the 7 meters and m is the total mass of the pumpkin. Our final energy is equal to kinetic energy plus potential energy. In this case, the kinetic energies are the energies of the pumpkin as it blows outward. All right? It doesn't matter that they're not in a vertical direction. That's still a speed, and that's still going to contribute to the kinetic energy. So this is going to be 1/2 times the 20-pound piece times its speed squared plus 1/2 times the 80-pound piece times its speed squared, and plus the potential energy, but if we assume the ground is 0, that's a 0, and that gives us a total energy at the end. Now, we're explicitly told that we can assume that the energy is conserved in this collision, so we can immediately set that equal to each other. And now we've got a relationship between the two speeds and mgh. And we also have a previous relationship between those two speeds. So let's write everything out in terms of our 20 meter, the speed of the 20 pound piece of pumpkin. So we're going to have 1/2 times m20 times v20 squared plus 1/2 times m80 times v80 squared, but that's just 1/4 squared times v20 squared, and that's equal to our total mass mg times h. All right, so let's simplify this a little bit. We're going to put v20 squared all on one side. If we multiply by 2, and then we can essentially divide by the combination of the 20-pound mass divided by plus a 1/16 of the 80-pound mass. So that's going to be 2 times mgh over m20 plus 1/16 m80. That's the total speed squared. And we can go ahead and solve for this by putting in some numbers. Take the square root, so this is going to be 2 times 9.8 meters per second squared times the height, which is 7.0 meters, times the total mass of the pumpkin, which was 45 kilograms, divided by 20 pounds, which is 0.2 times 45 kilograms, plus 1/16 times 0.8 times 45 kilograms. All right. Lots of numbers, but it's not too hard math. We can see that we're going to cancel out our kilograms. We're going to have meters squared per second squared, which if we take square root is our meters per second. And we write all these numbers down, we're going to get a number of about 23 meters per second for the speed of the small piece of pumpkin as it shoots out upon impact. And just to get an idea of how fast it is, remember it's about 2 miles per hour per meters per second, so this works out to be about 50 miles per hour, which is indeed a very fast piece of pumpkin, particularly if it's 20 pounds coming at you. So as someone being mindful of the safety of the observers of the pumpkin drop, you may want to make sure that people stand back quite a bit so they don't get hit by 50 mile per hour pieces of pumpkin coming at them. Now, of course, that's an upper limit for the speed for this kind of problem. Again, we made a really big assumption to say that the energy is conserved in this collision when we know for sure that there's a loud impact, and of course even the act of tearing apart the pumpkin on impact is going to take up a lot of the energy from the original fall. So this gives us an outside estimate of what the speed is, but it's enough to sort of give us an idea of how far we may want to stand people back in order to watch the pumpkin drop. So I hope you've seen now how we can apply our momentum-impulse relation to solve any number of complex interactions, whether it's a pumpkin falling down on the ground or a car collision or all sorts of different things. The important thing is making sure that you follow the procedures as close to this sort of step-by-step process as you can, because it allows us to organize our information. So good luck with solving your momentum impulse problems, and take a look at some of the other videos to see how we solve problems using momentum impulse and some of our other physics quantities.